Hi, welcome to the presentation of similar data mining similar topic. My name is Sai Krishna and my topic is efficient learning and deep learning through evolutionary computations. So the first is artificial neural networks. Um, this is what we use to train a typical network. It has a series of input layers and then output layers and the hidden nodes to capture the knowledge of the data. Um, Typically, feed-forward networks are used, but the problems are choosing the right number of hidden neurons and layers, and there is also a lot of sparse connections. Of course, it depends on the nature of problem, and then the most common approach that is used to train the neural networks is the backpropagation with stochastic gradient descent. However, this is a statistical method and hence suffers from local minima problems. It also has high training time. Some There is also a concern that the amount of training data required is high for modeling, and this is particularly if the network is very large. And then there are also generalization problems based on the how you choose the hidden layer architecture. So in this case, you can observe that there is only one global minima, and since because it's only one dimensional, there is only one global minima, and you can expect gradient descent to fall into the global. However, if you look at this case, there are multiple local minimas and there is only one global minima. So depending on the random point you start, the gradient descent might actually end up in a local minimum. This is another example in a little higher dimensional space. So evolutionary algorithms are population-based optimization algorithms, and these are mainly used for solving NP-hard problems, and they actually require more computation power compared to statistical optimization methods, but they offer like better convergence and then better optimization value. So the most common one is used is the genetic algorithm. It's so it is inspired from the Darwinian theory of survival of the fittest. So the fittest one survives and then becomes the part of the next generation. Various operations that are part of genetic algorithm are mutation, crossover, and reproduction. There are also other algorithms, evolutionary algorithms like particle swarm optimization inspired from the swarm behavior, and then ant colony optimization to find the shortest route. Each evolutionary algorithm has performed better in one or more specific domains. So let's again come back to the neural network training. So since we determined that the weights and the layers also to be optimized, and then that also determines the quality. Um, Topology and weight evolving neural networks are already present in most standard literature. They optimize topology in addition to weights, but this creates more variable to optimization. And then there is also a mixed integer optimization problem because you have to optimize whether it's present or absence of the links. However, this solves the problem of finding the right number of hidden neurons. So the most famous method in um, topology and weight evolving neural networks is the neuroevolution of augmented topologies. This supports the concept of multiple species. So the lesser species are protected and then given time to evolve during the concept of speciation. So there, it actually maintains the diversity and also helps in um, optimizing the topology better. So this is an example of how NEAT works. You can observe that there is a parent 1 and then parent 2. So when both are getting crossovered, generally the fittest parent gets the output if they are having contradictions. And if there is no link present, the link is added and so on. So you can see that the extra links are added in the child, and then the um, weight of the strongest parent has been taken in the genome. So the advantage of NEAT are typically it solves the problem of right number of hidden neurons, and then it also helps to solve multi-object optimization problems thanks to the concept of speciation. However, it being a topology and weight evolving neural network, it inherits the disadvantage of those. It's a more complex problem, more variable to optimize, and it's also a mixed integer optimization problem. So hybrid models can actually work better, and then there is a concept that you can use Uh, so since we determined that back propagation is can get stuck in local minima, back propagation is actually a better local learning algorithm. So you can use neat for global learning and then back propagation for local learning, thus actually optimizing the behavior of both. And then there is one example in the literature where they used hybrid model. um, this uh, paper reports that they got a 5% improvement by doing um, a more combining neat with LSTM specific mutation searches. So again, the hybrid model variations can be fine grained. It means it can be at the link level, or also it can be coarse grained. It can be at more broader level in optimizing multiple algorithms and likewise. So let's come to the methodology. Um, the process that is used, the training process overview is present here. So we get a data set and we get an output model, and in between we have a training configuration. So the training configuration again consists of three more components. The first one is a training algorithm, second one is network model, and then the third is a parameter control. Training algorithm ensures that the model is actually trained properly based on the outputs it's received from the training model. The parameter control actually optimizes the dynamics of the system, thereby ensuring that it's not get its local minima or maintaining some diversity, or also satisfying um, model constraints and environmental constraints. So yeah, the training algorithms that are considered so far are genetic algorithm, particles form optimization algorithm, back propagation, stochastic gradient descent, and then a hybrid algorithms based on the parameter control. So again, the interactions are training the network model and then collecting the feedback from the network model and then updating the training state based on the parameter control. This can be like updating the crossover rate, mutation rate, population size, or also switching to a whole new training algorithm. The network model has again different topologies. They can be divided into simple topology, complex topology, and probabilistic topology. So the interactions are like receiving the training parameters from training algorithm and updating them, and then sending the quality metrics based on the new architecture, and then again also sending the state information and metrics to parameter control component so it can take better decisions, and then also ensuring that if any other parameter configurations are received and then being updated back in the model. So this is an example of simple topology where all possible connections are present. And then this is a complex topology. Both consist of 5 nodes, but you can see like there are a lot of links that are not present. This is because the topology is also optimized in this case. Probabilistic topology is somewhere in between both of simple and topology, complex topology. Um, the existence value, the value that the link is present or not, is determined by the following transfer function. So you can see like when the probability is 1, the link is actually present, and then when the probability is 0, link is not present. And then the existence is actually determined by smoothing factor. This, based on the smoothing factor, it can be very discrete to very continuous. But the disadvantage again, it creates additional non-linearity, so more time to optimize. The next part is the parameter control. So the object of the parameter control is to collect the feedback from the system and then assess the quality of the parameter values. This can be like how good the best solution has been improved, or how the overall mean has been improved in the population. Also assessing the quality to the parameter values. This is the part where over a few generations did the parameter values actually bring up a positive change or a negative change, thereby capturing the whole information as a knowledge. And then based on the knowledge, a decision can be made to whether explore or exploit the parameter space. Exploration involves searching new parameter space and then obtaining the knowledge back so that you can take better decisions in the future. Exploiting is like using the existing knowledge to actually force the behavior of the system to a more positive state. Based on the above decision, new parameter values are generated and then the communication is sent back to the appropriate component to update the parameter values. So, before going into deep results, let's start with some preliminary evaluation. This paper introduces that for this particular network and for the XOR data, there is a local minima using backpropagation. So let's first try to replicate the results. So using backpropagation, we can see that the mean square error is saturated at 1.2, while the gradient has become close to 0. Now training is done using genetic algorithm. We got a best of 0.002 of the same for the same network. Thus, using genetic algorithm, we have successfully avoided local minima. Next, we change the topology to simple case using 5 nodes. In this case, we can observe the value is far more better, so the fit is even more good. Then we moved back to 4 nodes because we prefer, like, generally the simpler model is the better. So let's see, like, if 4 nodes, how 4 nodes perform. So it also performs well. Next, we optimize the structure as well. The quality dropped a little, but the final output is still a lot better than the back propagation. You can see that the number of links are far more reduced, thus better memory optimization. This is using particle swarm optimization, again using 5 nodes. The results are actually better than a genetic algorithm. So now we can move into more high-level data sets which are used in more real time. So the data sets that are considered are like iris and then the power plant. So this is a classification data and then this is a regression data. So the architecture that is involved is like creating a sample length vector, which is varying the sample size from small to large, and then observing the performance, like how it performs at small sample size of training data to large sample size of training data, and then same the common training data for all the configurations, and also common validation data, which is the whole data set used, and then 10 repetitions are used to avoid some bias on the training data. The configurations that are considered are back propagation with hyperbolic tangential sigmoid activation and then logarithmic sigmoid activation, and genetic algorithm with simple topology, particles form with simple topology, and then neat. So let's start with the regression results. So you can see that neat actually performed pretty well for the regression at lower samples. And as the number of samples increases, the results are almost similar, but a closer look actually says that neat actually performed the best of all. This can be attributed because of the simple topology. There are a lot of output connections, and then this creates a lot of variance for particularly small data. So this can be expected. But now let's say, like, if we restrict only for 200 epochs, because we can also use the concept of parallelization in case of evolutionary algorithms. Such, it's stated in one of the papers mentioned in references that one generation is approximately equal to one epoch if we actually end up using GPUs. So if we force back propagation to stop at 200 epochs, we can clearly observe that the results are far better for the evolutionary algorithms. So let's put a little more leniency, and let's say, like, allowing a 500 epochs. Still the results are better for the evolutionary algorithms. Let's start with the iris dataset. So this is the mean and accuracy and standard deviation for various sample size. The sample count is for per class. We can clearly see that genetic algorithm and particle swarm optimization has very high accuracy and very less standard deviation. Um, the standard deviation actually tells you how reliable the algorithm is. However, NEAT actually failed to perform well in this case. This can also be because that it's a topology evolving algorithm as well, so it might need more training time, but more on this can be only obtained by further research. So again, restricting back to 200 epochs, we can clearly see that there is a large gap between the back propagation algorithms compared to evolution algorithms. And then increasing a little further to 500 epochs, the performance is not that much improved. Still, the evolutionary algorithms perform a lot better. So the conclusions is like we can say that evolutionary algorithms are capable for finding better solutions compared to backpropagation. And then the results from XOR show that the limitations of backpropagation, particularly in finding global minima, whereas the results from Iris and PowerPlan dataset shows that evolutionary algorithms can perform particularly well at low training data sample size. So this actually works better for one-shot learning or few-shot learning cases. So in case of classification, PSO and ZA performed well, whereas in case of regression, NEAT performed well. The other thing conclusions we can draw from here is like uh, the evolutionary algorithms contains a lot of parallel parts, so this can make a large um, impact and interesting prospects for the future research in case of evolutionary algorithm training for neural networks. Thank you.